Yes guys, welcome back to PR Math School. Today we are still continuing with our introductory work. That's our 8th part right now, three-dimensional trigonometry. And these are the things we're going to briefly look at under this three-dimensional trigonometry. We're going to look at the angle between a line and a plane, angle between two planes, line of greatest slope, angle between skew lines. Then at last we're going to look at examples that will require us to get angles or between all these four situations: plane and line, two planes, line of greatest slope, which will also involve angles. Then we look at angle between skew lines. So let's start with the first one, that's angle between a line and a plane. The first one, angle between a line and a plane. Now let's draw an example. Let me say a plane. Let's say we have a plane here, something like that. We can join that. Join this also. Assuming this is a plane, let's say A, B, C, D. A plane, I just mean a surface. Let me bring an example. This could be one plane, a plane. So it's just one surface, which is a plane. Meanwhile, a line is just something which is of, let me say, from here to here. This could be a line. Okay. A line can also be, let me say, this pen. That can be a line on that can represent a line. A line is just a stretch of a thin or a thin drawing, which a prolonged thin drawing, which would mean we will be representing a line. We can have something like that to represent a line, while for this case we have plane. Now, angle between a line and a plane, let's assume that we have this as our plane, and now we consider this pen to be a line. Now the angle between, let's say, this pen, which is a line, is meeting this plane at a point. Let's say at this point, the angle between this line and the plane will be, and let me say we draw, and now we put a shadow of that line down here like this. Okay. So the angle between this plane and the line, this one is actually basically on this plane, the shadow. So the angle between it will be the angle between the line, which is its shadow here, the shadow, and the angle between that real line. That means the angle between this plane, we draw a line on this plane, and we consider the distance, that angle between this line and that plane, that gap there will be our angle. Then we can consider that there are another line is maybe joining, coming from the top of that, then falling on this line at right angles, on this plane at right angles, something like that. Let me say this, something like that, whereby this angle and this is 90 degrees. So we are going to consider draw such a thing in our diagram. Let's say we have the line is meeting, let me say, this at this point, and let me draw it something like going there. Remember, when I was demonstrating with a pen, that it's just standing at that point like that, not basically lying on it like that, like the way you see the line. It's not like that. So now we name this to be, let me say, P and Q, and we draw another line on this plane, the one now lying on the plane itself. We can draw another line, let me say something like that. Okay, it's on the plane, and we now maybe drop a perpendicular to this point. Say that line joining that line coming to this line on the plane is meeting the plane at 90 degrees. Okay, we can give this point O. Now the angle between the plane and this line is actually the angle between this shadow. This line is a shadow of that line PQ. PO is a shadow of PQ, which means the angle between this line is actually on the plane itself. If this is the plane, the line is actually on the plane, while there's another one pointing like that, something like that. Okay, whereby there's an angle here and there's another line joining them at right angle. So the angle between this plane and this line is actually this. Okay, which we are going to be seeing here. We can give it angle. The angle, we say that the angle between line and the plane is QPO, where P is that, we can put that to be theta. Okay, where this at right angle to the plane, and this shadow is on the plane itself. And now we can go to another condition. Let's say 2, angle between planes. We say this angle between planes. Now for this case we can have let me say let me draw something like this. Okay, something like that. Okay, then we join that. Then we draw another one here. And you try to join that. Okay, let's consider this line to be AB. This line, I'm going to name this, maybe say this one here S, from here up to there R. Okay, then we consider here to be, let me say, A, B, C, and D. Okay, then we draw a perpendicular to this line, and also perpendicular to this line. To this line AB. Let's say this is 90, meeting that line at 90, even here meeting that line at 90. I might not have drawn it perfectly, but like that. And we also consider this, and we also consider that to be, say, theta. Now let's consider this to be one plane, this one up here. Okay, then we can also see that this one here is another plane. Now these planes are joined. I can demonstrate that from here. We have that. Let me fold that into 2. We have something like that. Okay, whereby this is another plane, that, and this another plane, being joined by a line in the middle. That folding, let me say, that folding is the one joining the 2 planes. But initially, if we separate, we would have maybe this one separate plane and this one separate plane. Now the angle between these two planes is just simply drawing a perpendicular line from that point up to there at 90, then that 90. Then we can name, maybe say, this line is L, this one M, then we make here to be N, something like that, N, so that we know that actually if we draw a line here and a line there, the angle between these 2 planes will be actually the same as the angle between these lines. Why? Because these lines are just perpendicular, like at right angles there, also another one at right angle. But when you fold, you see that there will be an angle between those 2 planes. Inside there will be an angle, whereby this one, the angle between them will be actually the line meeting, those lines meeting on that line AB, which will be the angle between these lines will be the same as the angle between these two planes, because these lines are on the planes. And so we can say here the angle between the planes is given by L N M, which is this theta here, because that line is actually the line perpendicular to those. So it's like I demonstrated like a line drawn here and another line drawn here, and they're meeting at this point on line AB. So the upper line of intersection is actually AB, and their point of intersection is this N, where their perpendiculars meet. So the angle between these two planes is actually this angle, or can be the same as this angle. When you fold it, a paper like this, you can know that the angle is this. Now we go to the third one. Line of greatest slope. The line of greatest slope. Now for this case, we're going to have an inclined plane, whereby let me first try to draw it. Let me have something like that, something like that as well. Try to join here, then we try to join there. Let me say I draw something, the height of that plane, of that inclined plane. Then we say this is what, 90 degrees. Okay, so let's say that's an inclined plane, I mean a slope. We have, first of all, let me give something like this. We have something like that, whereby this side is sloping. It's not straight like this, but it's sloping, something like that. Then behind here, behind here we actually have the height of that slope, like the distance from the top of the slope up to the base of the slope, or up to the horizontal ground. This are ground, like you just have a slope, or I can fold this and just put like that, a slope. This is the horizontal. So from down climbing out, and the height will be actually that distance from here, and that distance from here up to down. So that's what I've drawn here. I have something slanting that way, but there's a height which to the horizontal ground, which we can have something like that. And let us say that there's a point here. Let me say point O, whereby we have this point is at the base of the inclined plane, and we have, let me say, let's draw an horizontal line there, which would try to let it mean it's on this plane. Now we draw a line to, let me say, a point A. Okay, another line to, let me say, a point B, and another line up to the point C. Now we are going to see that, let us now give that like that, that's a point. From that point up to this base here, up to the horizontal level, we have actually height from that point. That height is these 3 points here are the same height. If you go down, that means if you drop down, let me say, I can try to give that dot like to mean where the height of that from there up to there, that's the height of the inclined plane. And now we drop a perpendicular from each point up to that point of the height there, then up to there, whereby these ones are meeting that base or that horizontal surface at 90 degrees, even this, and we give that height h, which is actually the height of the inclined plane, which is also h from that point. Now Okay, then maybe this one is starting at a point because the height of the inclined plane is there. Let's give maybe height of inclined plane to be capital H to differentiate. Now we have, let's join that point up to this, each one of these points there. That one also I join to this point for OB. Then also this one join to there. So that we have the height, the adjacent, and the hypotenuse, and whereby we have an angle here, let me say theta 1, another angle for between OB and its thing and its adjacent, say theta 2, and for OC and its adjacent to be theta 3. Okay, now we have that. We are going to see which of this line is the steepest. Which of the three lines is the steepest or forms the greatest slope, or which of these three lines is harder, is harder to climb. Like if you're climbing from O to A compared to climbing from O to B compared to climbing from O to C, which one can be harder for you to climb in case you're climbing from the bottom up to the top of that inclined plane. Now let's consider that this angle here, if you can observe that we see this length OA, OB, and OC. If you observe carefully, this line is actually longer than, shorter than this other line. So we can say that line OA, let's put that to mean line, is actually less than OB and at the same time less than OC. Okay. Now we are going to see that if you want to understand that height properly, let me draw another one which can be easier to understand here. Let's say we have that as a plane inclined. Okay, that inclined, let us name that ABC. Let that ABC be here, A, B, and C here, and our point O is here. Okay, we join those, we join that, and we also join C to the base. Remember the base here at this start here is actually the same height up to there. If I join that, I just connect down, you can really see that's the same height I'm meaning here. But now this one I was showing in 3D, some bit of 3D, but here I'm just showing in 2D that the height of that inclined plane is actually the height that comes to the base here. So if you want to see how that H is actually all those H heights are the same, just draw perpendicular here, drop that one also perpendicular here, and also drop the perpendicular down here. You realize that these angles, now this angle we are measuring, this extensions we are seeing is actually this is the same as that line down there, only that we were slanting it, but it's along that slant. Are you seeing? But same level and same height, I can say. So that angle is actually up to this point. That's theta 1. Theta 2, that first one. Theta 2 is actually from there up to that point also. And theta 3 is actually from this one up to down there, theta 3. Okay, you can see that theta 1, theta 2, theta 3 is bigger. And now we are going to show that here in this explanation. If we are to get that length OA in terms of sine theta 1, if we get sine of theta 1, it's the one that's going to consider, because sine we can't consider cos because we are going to have adjacent, which we don't know. We can say that we have height here, and we have that sine theta 1 is actually going to be the opposite, which is H, opposite to this angle, out of the hypotenuse, which is OA. Okay, sine theta 2, of which this height to each one was H. Okay, now sine theta 2 is actually going to be that angle opposite to that, which is opposite is H, out of hypotenuse, which is OB. And now sine theta 3 will be actually H, the opposite out of the hypotenuse, which is OC. Okay, Now, according to this drawing, you realize that this length is shorter than this, and this is shorter than that. The longest is actually C. Now, let me give you this. If you have 1 out of 1, okay, 1 out of 2, and 1 out of 3, you find that this is 1, this is 0.5, and this is something like 0.33 recurring. Now, you realize that as the denominator increases, the smaller the whole of that value is. You see that this 3 is bigger than this, but now a half is 1 out of 2 is bigger than 1 out of 3, because when we change that to a decimal to a whole number, or try to change to a whole number or decimal place, you will have 0.3. Here you have 0.5. Here you have only 1. So you can observe that as the denominator increases, the figure is actually the whole result is actually smaller. That means here OC, which is bigger, will imply that actually sine theta 3 is the smallest. It's the smallest of the 3. Because OC is bigger than OB, that means actually this one is bigger than OC. From this thing that I've shown you, 1 out of 3 is smaller than 1 out of 2. Yet 3 is bigger than. If you compare 3 and OC, will be bigger compared to OB. Now, if I give them, let me say 1 out of 1, 1 out of 2, 1 out of and then 1 out of 3 here. You realize that this will be smaller because the denominator is bigger. OC is bigger than the rest. OB is second, which is second smallest, second bigger, which makes the whole of sine theta 2 second smaller. OA is the shortest, which makes actually this the smallest, which means actually this actually the biggest. What does it mean? As sine theta 1 is going to be bigger than sine theta 2, and is going to be bigger than sine theta 3. Now we have sine here, sine here, sine here. So we just compare. That means theta 1 actually is going to be bigger than theta 2, and it's going to be bigger than theta 3. Now what do we observe from here? That means the line which is near almost. So that means actually you see that these angles, when the bigger they are, smaller, bigger, biggest. Now that means if it keeps extending up to a point, maybe when, let me say, it's straight, okay, I can draw that. Imagine now theta 3 is smaller compared to theta 2, compared to theta 2 is also smaller compared to theta 1. That means theta 1 can also be smaller compared to another angle. Let me say it increases up to somewhere here, it will be smaller if that extends. If this extends to maybe another angle, let me say another line is drawn there, this angle will be bigger than theta 1. So what does it mean? And remember, when you're climbing an inclined plane, if you try to climb it straight up like that, it will always, like here, have you ever seen when you're climbing a hill, as you try to climb it straight, it's always harder to climb compared to when you try to climb as slanting. That's why if you're climbing it straight, you always start sliding downwards, because you keep sliding where it's easier to climb. That's a simple way I can explain to you that. Now let us draw in a simple way how I can show you the steepest the line of steepest slope. So now that means actually our line of steepest slope will be when now that theta has increased to this point. Let's have something like that. Something like that. Let me draw something like that. Then something like that. That's our inclined plane. Then we draw its height. We assume its height to be somewhere there. That is 90 degrees. That's the height. Now we have a AB here, up here. Then we are going to show this like that. That's perpendicular to this, also perpendicular to that. You find that going straight there is harder compared to when it's slanting. Climbing straight is harder compared to when you're, so that makes this one the steepest line in slope, and it happens as theta increases until reaching 90 degrees. Because now if you slope this side again, theta is going to be again smaller this side, which will make it again easier to climb if you're going that side. But if you this side, that's the hardest way to climb the hill. So that actually means our line of steepest slope is when actually theta, we can say that plane, we say a plane is inclined at angle theta to the horizontal. We then, well, I mean, when we say that the plane is actually inclined at an angle theta to the horizontal, we mean that the line of greatest slope makes an angle theta with the horizontal plane, if you can see from here. So the line of greatest slope is now this one, which is maximum when theta has increased up to when it's perpendicular to this and perpendicular to the horizontal line. That horizontal line is actually parallel to this. So that's a line of greatest slope. So that means that actually we are going to have that. When we say now that the plane is inclined at angle theta, we mean that this to the horizontal, we mean this line of greatest slope is actually inclined at an angle theta to the horizontal, or makes an angle theta to the horizontal. And now let's go to the fourth one. I think we have understood the line of greatest slope. This is our line of greatest slope. Now we go to the fourth part, angle between skew lines. Now for angle between skew lines, we are going to see that we have we will check first of all. I think I need to first explain to you 3D, I mean 2-dimension situation, and I when I talk about a 2-dimension situation, we mean one plane. Let me say something like that. Only one plane like that. That is one plane. Just 2-dimension, in that you can only have, well, remember in 2-dimension we have only two sides. Let me say this is our x and this is our y. Now we have only two sides which actually are joined to form one plane. Now in 2 dimensions, that's in case of one plane. We mean if you have a line on the plane, let me say like that pen, lines don't only meet if they're parallel like that. Okay, so we have two non-parallel lines are the ones that intersect. Let me say now this one was going like that, not parallel. That means they're meeting at that point. If you keep pushing that, they will meet at some point. Now, but however, in 3D, that one now I mean when there are other planes. Let me say there is this plane, and I have maybe, okay, let me consider this surface of mine to be one plane, the surface here to be one plane, and another surface, say up here, another plane. Let me say I had a line on that plane, okay, and another line on this plane, going like that. Now non-parallel lines on a 3D or in a 3-dimension situation can only intersect if, okay, let me say that since these two lines, I think that one on that plane and this one in this plane, okay, if I remove, you see this one is in space. When I put that its plane where it is, these lines cannot intersect. Why? Because they're in different planes. But if they're in the same plane, like for the case of that, in one plane, 2D means one plane, they intersect. But if I take it back to its plane and it's in this plane up here and that one is down there, they can't intersect. Yet when you see from up, you might see they are meeting, yet they are non-parallel. For this case, we call these two lines skew lines. They are not parallel, but they are not intersecting. But they have an angle between them, that angle between them. Okay, so now that angle is the one that we can consider an angle between skew lines, so that if we cast the shadow of this upper line down there, we can see they look like they can intersect. Now that angle between them is the one we are calling angle between skew lines. But when this line is up, its shadow casting on that to look like it has crossed, I mean the lines have crossed, so the angle between them will actually be that. Okay, so that's angle between skew lines. Skew lines don't meet, yet they are not parallel because they're in different planes. If they're in the same planes, you would consider them. Once they're not parallel but on the same plane, we just know that they're going to intersect. or the for case of coplanar means same plane. When they're in coplanar when they're coplanar or on the same plane, they will intersect. But skew lines don't intersect because they are on different planes. Let me show you that in terms of drawing. Let me say I have a plane here. That's one plane. That's one plane. Okay. Now I have another plane, let me say up, whereby the line is just passing up like that. Okay, let me say a line is passing from up like that. Now let me just draw. I'm going to let it cross there, but yet in the actual sense it's not touching that plane, it's just up. I've drawn something like that. That line, don't consider it to be on the plane, it's up like this. Okay, let me block it. Something passing like that. So that is just skew, it's just on top of that. It's in a different plane. If I put like I did before, it's on a different plane. Okay, but if you remove that, it's plane, you see that it's on that plane, yet is not what I mean. Now let's say name that line P Q. It's not touching, it's not on that plane. Now let's cast its shadow here. Okay, and we join. In that is parallel. I've not made it perfectly parallel, I think, the drawing, but let's assume it's parallel because this is a shadow of that, should be parallel. Let's name that A B. Okay, now that AB, let us now consider a line on this plane, that a line which is on this plane, let me say LM, which is not parallel to this. It's not parallel to that line, it's just on this plane, not parallel and not meeting that line PQ, but is crossing the shadow of PQ like I demonstrated before. Let's give it, let me say LM. So now that makes that the shadow of this line, which is AB, is actually looking like it's above, but it's looking like it's crossing. It's crossing the like it's looking like that line is crossing this line on the plane. So the angle between the skew lines is the angle between this a line which is skew to the line on the plane, not parallel but not also but not meeting. So the angle between them is actually this angle, which is the angle between the shadow of PQ and the line on the plane. So the angle between PQ and LM is theta, okay, which is the angle between the skew lines. Skew lines. Actually no, let me say AB because it makes AB and LM is theta, which is the angle between skew lines PQ and LM on the plane. Okay guys, thank you for coming to this channel. I think for today we are done, and in the next video I'm going to do for you examples that involves finding the angles between these lines, skew lines, between line and plane, between planes, and maybe line of greatest slope if you have any example close to that. Thank you for coming to my channel. Please like, subscribe, share, and don't forget to comment. See you in my next video when I'm looking at examples to this that we have covered today. Bye.